about the radiation budget, what the Earth does with incoming solar radiation, and we've talked a lot about absorption and reflection, but one thing we haven't talked about yet is called scattering. So, for us to understand the concept of scattering, we need to understand that not every beam of solar radiation is equal. Rather, beams have many different wavelengths of radiation, and each one of these wavelengths has a corresponding color. Well, at least when we're talking about visible light. And I've mentioned this before, but the way that this works is shorter wavelengths end up having colors such as violet, indigo, and blue, whereas longer wavelengths have oranges, reds, and deep reds, and so on. So if you remember learning about Roy G. Biv when you were a kid, well, your teachers told it to you backwards. The fact of the matter is, using wavelength, putting them in order of wavelength, it actually starts with violet and ends with red. So the shortest wavelengths are over here, longest wavelengths are over here. Now what I want you to know though is that different wavelengths correspond with different colors. And a beam of solar radiation has many different wavelengths to it. And when one of these beams of solar radiation hits something, the light that isn't absorbed or reflected is what's called scattered. And in particular, certain droplets, certain cloud droplets and also certain gases in the atmosphere will actually take a beam of sunlight and split it up into all of those individual colors. All of those individual colors. Now specifically, when talking about clouds, large cloud droplets, so droplets around 10 micrometers or larger, and if you remember, we've talked about micrometers in the past, and a micrometer is just a really, really, really tiny distance. However, these cloud droplets are larger than 10 micrometers in diameter. These cloud droplets do a good job of effectively scattering all wavelengths of visible light. Pretty much all wavelengths pretty much equally. And so when a beam of sunlight hits it, all of those different colors come out. They are scattered out by the light. Now, with that said, many cloud droplets aren't that big. Believe it or not, most cloud droplets are really tiny. And so rather than scattering all of those individual colors, instead, they scatter them all together, creating white light. That's one of the reasons why clouds are white, because clouds usually consist of these really tiny droplets that scatter white light everywhere. That scatter them almost everywhere. However, the larger the cloud droplet becomes, the better it is at scattering all colors in all different directions. All colors in all different directions. However, the bigger a drop becomes, it's also able to do something else. It's also able to absorb it. And so if you've ever looked at a dark, angry, stormy-looking cloud, the reason why it's dark is because those cloud droplets are so big, they do a really good job of absorbing most of what hits them. Meanwhile, on the top of those clouds, any light that hits it is usually scattered away. And so this is one of the reasons why the base of clouds are usually very dark. The next thing I'll talk about is the age-old question, why is the sky blue? So, when I talked about scattering, so far I've only mentioned a water droplet. However, all of the gases in our atmosphere also do a really good job at scattering different wavelengths. Now, our atmosphere is primarily made up of nitrogen and oxygen, right? Nitrogen and oxygen that make up 99% of the gases in our atmosphere. Well, believe it or not, those gases do a really good job of scattering blue light the best. On the other hand, other different wavelengths of light, such as red, yellow, green, aren't scattered as well by these gases. Well, because blue light is scattered the best by these gases, that's what these gases appear to us as. They appear to us as blue. And hence, this is why our sky is blue. All the gases in our atmosphere do a really good job of scattering blue light. Now, on the other hand, this is usually during midday. What about in the evening, though? The sky doesn't really look blue during the evening. No, instead, it usually looks orangish or red. Well, here's why this is. When the sun is lower on the horizon, like it is at night, or like it is just as the sun is setting, and also when the sun is coming up, the light from the sun actually has to travel through a lot more atmosphere. And the reason why is because as it's coming in from a low angle. So rather than coming straight in, it's coming in on a much more gentle slope, and so it has to travel further. Well, as it's traveling through the atmosphere, in this case, that sunlight hits the top of the atmosphere, and all that blue light is scattered away. The remaining light, the light that wasn't scattered, as it approaches the surface, is then scattered by everything, by all the gases in the atmosphere. But at this point, all the blue light's been scattered away. So the remaining light is yellow, then orange, then red. And so by the time this light reaches the surface, it usually looks orangish and red. So that's why the sky is orange or red at sunrise and at sunset when the sun is lower in the sky. It's because the sunlight has to travel through much more atmosphere, and all that blue light is scattered away.